Hi, everyone. Welcome. We're very happy to welcome Eliza Kempton today. She's our new neighbor at the University of Maryland. She got her PhD at Harvard in 2009, and then she was a Sagan Fellow at the University of California, Santa Cruz, before taking a faculty job at Grinnell College in Iowa. But Maryland has lured her away from the plains of Iowa to, unfortunately, I guess, the snow and ice of Maryland in the last couple weeks. So she just started at Maryland last fall. She's had quite a distinguished career in her time as faculty, including getting an NSF Career Award in 2017. I was happy to serve with her last year on the Exoplanet Strategy Committee of the National Academies, where she was a great, intelligent, enthusiastic, and organized contributor to that committee. So we're happy to have her in the neighborhood and to have her talk about exoplanet atmospheres.
Is this on? I guess it is. Thank you, Alicia, for that lovely introduction. I haven't been here for quite a while, but I have been to the campus here before. When I was a grad student, I worked with Sarah Seeger when she was still here. We worked on building some of the first models of the atmospheres of extrasolar super-Earths. And that's actually primarily what I work on, is super-Earths. But today I'm going to talk about something a little bit different. I'm going to talk more about hot Jupiters, highly irradiated giant planets. I want to first acknowledge my collaborators on everything that I'm going to present here today. Of primary importance, Emily Rauscher she's faculty at University of Michigan. She runs most of the 3D general circulation models of the hot Jupiters that I'm going to present spectra of. And Emily and I have been very fortunate to have worked with a long line of very talented undergraduates, many of whom have now gone on to graduate school. So I'll be highlighting the work of many of these students throughout the talk. Okay, so hot Jupiters. Why do we care about highly irradiated giant planets? These objects are very interesting in terms of being a laboratory for exotic planetary physics, right? We don't have analogous objects in our solar system. You'd have to pick up Jupiter and move it all the way in to a 3-day orbital period to simulate one of these objects. But we're lucky that nature has provided us with many of these objects so that we can sense them remotely as exoplanets. Because these planets are very close into their host stars, the tidal synchronization timescale is very short relative to the typical age of these systems. So these planets are expected to be tidally locked to their host stars. So now they're very close in, and they have a permanent, very hot day side, but potentially a night side that's much, much colder because it does not receive any direct irradiation. And both observations and models imply that the atmospheres of these objects can be very exotic, right? You have gas at 1,000, 2,000, 3,000 plus Kelvin. And what that means is that the species that are typically locked away in solid phase in the planets in our solar system are in the gas phase in the atmospheres of these planets. So you can directly detect molecules like water, methane, carbon monoxide, et cetera, potentially nitrogen species that in the giant planets of our solar system are mostly, can be locked away in deep clouds or in the interior. Additionally, for the very, very hot, for the most highly irradiated hot Jupiters, you even have refractory species in the gas phase. You can even have metals, like true metals, in the gas phase. You can have clouds forming from materials that you would typically think of, on Earth as being locked away in rocks in the interior of the planet. So some of these planets are expected to have clouds of, say, iron, enstatite, silicates, et cetera. So these are exciting exotic objects to observe and study. And from a practical standpoint, hot Jupiters are the easiest exoplanets to observe, in a sense, right? They're the hottest objects, and they're large. So atmospheric characterization studies, which are typically very challenging because you're looking at the planet relative to its huge, bright host star. These are the easiest objects to access, and therefore we're going to be able to do the most detailed studies first on these planets. All right, so with that high-level motivation, I am interested in understanding hot Jupiters and exoplanets in general in their full 3D glory. So with exoplanets, I often model these planets as one-dimensional objects. Right? We have just one-dimensional, say, temperature pressure profile through the atmosphere that is meant to encompass the global average of the planet. And that's actually, you might think that's actually okay for exoplanets because we don't resolve the sources. And so just treating them as kind of a global average planet, that could be okay. But these are 3D objects, right? And we need to contend with that. And we're really going to need to contend with that in the upcoming era of JWST and 30-meter class ground-based telescopes. Okay, so what do we expect of the 3D properties, the 3D atmospheric circulation in hot Jupiters? There are quite a number of modeling groups that do general circulation models of these planets. Each group, interestingly, they all make different choices in the level of complexity of physics and chemistry that they include in their models. So in a sense, it's comforting that all of the key groups seem to predict the same big picture properties of the circulation regime in these planets. So I'll just step you through the key predictions. And I'm climbing up through the planetary atmosphere as I go. So at the infrared photosphere or below, you set up, the prediction is that you set up just one primary jet, super rotating jet around the planet. So this is different from Jupiter. We picture many individual bands around the planet. Here you just get basically one band, and that comes from the fact that these planets are, because they're tidally locked, are much more slowly rotating than Jupiter and also more highly irradiated. That puts you into a regime where you expect a much broader, almost planet-scale jet band around the planet. And as you climb up through the planetary atmosphere now, around the infrared photosphere, you expect, because of that super rotating jet, you're going to advect the hot gas away from the substellar point of the planet eastward in the direction of the planet's rotation. So we expect that the hottest point of the planet is going to be located to the east of the substellar point. That potentially has observable consequences. And higher up in the atmosphere, at pressures of closer to a millibar or so, you're in a regime where you just get direct day-to-night flow. So the gas from the circulation is directly from the hot day side of the planet around to the colder night side of the planet, just directly moving heat to the night side. Let me ground you here. So I'm going to be talking a lot about observables through the rest of the talk. When I'm talking about thermal emission spectra, we're looking around here. So we're going to see that we should be looking for the effect of the eastward shifted hotspot. When I'm talking about transmission spectra, we are looking higher up in the planetary atmosphere, and we're going to be probing the regime where the flow is directly day to night. So try to keep that in mind as I move on. Okay, so observationally, we probe atmospheric circulation using two key techniques. The first one is through phase curves. The second technique is through doing high-resolution spectroscopy, and I'm going to walk you through both of those techniques and what we can learn from each of them. I'm going to focus primarily in this talk on the second one, though. Okay, so phase curves are, this was the first way that we got any information about the 3D temperature structure of a hot Jupiter atmosphere. So this is actually the first infrared phase curve observation taken by Heather Knudsen in 2007 with the Spitzer Space Telescope. It's a very famous observation. So what you're seeing here, this is the flux from the planet. And this is HD 189733b. So this is a canonical hot Jupiter. This is the flux from the planet as a function of its orbital phase, and they observed the planet for one full orbital period. So you see the night side of the planet. This is transit right here. It goes off the scale. The transit dips way down. At transit, you're seeing the night side of the planet, and then the planet orbits around, and the day side of the planet comes into view right before the secondary eclipse. So this is actually the secondary eclipse when the planet disappears behind its host star. So remember, these planets are tidally locked. If the heat transport from the day side of the planet to the night side was extremely inefficient, you would expect the amplitude of this signal right here to be equivalent to the depth of the secondary eclipse. That would be saying that the night side is at 0 Kelvin and the day side is just re-emitting everything that's hitting the planet. Instead, we see a much shallower phase variation. This is real. This is a real variation that they're seeing, which is showing us that the day-to-night heat transport in this planet is fairly efficient. A second effect that you may or may not be able to pick out by eye is that the peak of the phase curve variation is occurring before secondary eclipse. So that is saying what already came out of the prediction, which is that the hottest point on the planet is coming into view before the substellar point, or that the hottest point on the planet is shifted to the east on this planet by a number of degrees in longitude. So phase curves basically give you longitudinal information about the temperature structure of the planet, as well as information about the efficiency of day-night circulation. About, I think, 2-ish days, I think this one's 2.2 days. K-star, I think. Okay, so that was one planet. We've now done this for many, many more planets. Spitzer, the warm Spitzer mission has been really nice to studies of exoplanet atmospheres. So this is now, I'm looking at those same properties, the hotspot offset in degrees, and this is a parameterization of the day-night flux ratio, measured for something like 15 individual objects. And you can see potential trends that start to emerge. So the red lines here are predictions from an analytic toy model. Basically what we'd expect is for the more highly irradiated planets, the radiative timescales are relatively shorter compared to the dynamical timescales. And so for hotter planets, you expect that the day-night heat circulation is less efficient, and therefore you also expect that the hot spots are going to be less shifted for the hottest objects. And maybe we're seeing that, maybe. What would really help now, because the data still are a bit of a scatter plot, if we could fill out this diagram with even more objects, hopefully we could see the trends emerge more clearly. So we actually have data in hand from 2 different Spitzer phase curve surveys, one led by Kevin Stevenson and one led by Jacob Bean, that are going to more than double the current sample of hot Jupiter phase curves. And so that's all of these stars are just indicating the temperatures of the objects that, for which we have data in hand. And hopefully within the next year or so, be seeing some papers coming out that are really filling out this diagram and hopefully illuminating the trends, although with exoplanets, that's not always what has happened. So this remains to be seen. Let's leave it at that. Okay, so like I said, I'm actually gonna finish with phase curves here, and I'm going to spend most of the rest of my time talking about the other technique, which is a little bit newer on the scene in terms of trying to constrain atmospheric dynamics in hot Jupiters. And this is using high-resolution spectroscopy, and in particular looking at Doppler shifts in high-resolution spectra to directly constrain the wind speeds in the atmospheres of these planets. So first, let me again go through the technique. So what are we trying to do? We're trying to directly detect the light from the planet now, and we're doing this at very high spectral resolution. The advantage here is that the planet is orbiting, and for close-in planets, they're orbiting fast, and so the spectral lines from the planet are moving, and so they're sweeping in and out of both the telluric spectral lines. We're doing this from the ground now. High-resolution spectrographs are all on the ground. We're doing this from the ground with large telescopes. The planetary lines are sweeping in and out of the telluric lines, and they're sweeping in and out of the stellar lines. So we should be able to, in principle, disentangle the planet spectrum from the star and from the Earth. Of course, the planet's spectrum is very minute, it's very low signal to noise. So what we have to do is turn to cross-correlation techniques. So we're basically going to take the entire spectrum that we've obtained, but the planet spectrum is at such low signal to noise that we can't even really see it. We just see what appears to be noise. We take that whole spectrum and we basically collapse it down in velocity space. So we do a cross-correlation against a template, and we find where there's signal against that template, and that tells us that we've found the planet's atmosphere. Okay, so this is where I come in, because I model exoplanet atmospheres. And what is your template? It is a spectral model. So your model, your recovery of the planet's signature from the data is only as good as your model that you provided as the template. The better your model fits your actual data, the better you're going to recover the planetary signal. So we need accurate models of hot Jupiter spectra at very high spectral resolution. Okay, as someone who studies exoplanet atmospheres, I am much more used to, right now, I'm still much more used to seeing spectra that look like this than anything that would look like this. So this is a more typical hot Jupiter spectrum that is a transmission spectrum returned from HST, from the WIFC-3 instrument on HST. You can see this. So this is a detection of water in the planet WASP-43b. You can see this nice water band. It's detected at very low resolution. So there are many, many, many individual spectral lines that make up that water band, but we just see the band structure. So we can get the strength of the band and interpret something about the abundance of water in this planet's atmosphere. If you are instead observing at very high spectral resolution, resolving the individual lines, and let me ground you. So very high spectral resolution, I'm talking about hopefully approaching R of 10 to the 5, maybe even higher if we're lucky. But the instruments that are being used right now have resolution approaching 10 to the 5. Okay, so at R of 10 to the 5, you can actually resolve the individual lines that make up the molecular bands. And so in principle, you can probe the line profiles, the line shapes, and that gives you access to all kinds of information about the velocity field of the gas, the temperature structure of the gas, et cetera. So you can potentially do real line diagnostics on these spectra and get a lot of information out if you do it correctly. Okay, this is the first detection of an exoplanet atmosphere, a hot Jupiter atmosphere, using the high-resolution spectroscopy technique. This is coming from Ignas Snellen. His group has been really instrumental in getting this technique off the ground. It's really still on the ground, but anyways. So this is for the hot Jupiter HD 209458b. They've detected carbon monoxide in transmission, and let me step you through what this means. This is the color scale is the strength of the cross correlation of the data against their template model. as a function of orbital phase. So the signal that you're supposed to pick out is this dark diagonal line here. It's been enhanced here so you can see it a little bit better. So what is that? That is, the velocity is changing as a function of orbital phase. That is the orbital motion of the planet that they're picking up in cross-correlation in the CO band. The great thing is we know the orbital motion of this planet already because it is a transiting planet that is detected through radial velocities. So we know where that signal should be. We know how fast that planet's moving and what phase we're observing it at, and it's right where it's supposed to be. So that is the planet. That is definitely the planet, even though it might look like it's kind of low signal to noise still. It's at the right place. The slope is correct for the known orbital motion of the planet, but it's offset by a little bit. 2 kilometers per second plus or minus 1. So there's a potential 2 sigma detection of a systematic offset in the velocity of the planet. And what could that be telling us? Blue shifted. Well, this is transmission. We're seeing the absorption through the upper atmosphere. If that gas were moving towards us at 2 kilometers per second, that would give you your extra blue shift. And that's exactly what's predicted from at least that systematic blue shift, that motion towards you is exactly what's predicted from the 3D models, right? We predict that the gas should be moving at millibar pressures. That gas should be moving from the hot day side directly to the night side, directly at the observer. So this is potentially a direct detection of day to night winds in the atmosphere of this planet. Atmospheric dynamics, we'll see. Okay, so this observation motivated us to start modeling these effects in more detail to see what the 3D models really predict and whether they're in line with the observations. Okay, so how can you cause Doppler shifts in exoplanet spectra? You can do it in a couple ways. So we just said that the orbital motion of the planet will induce a Doppler shift. The gas is moving with the planet. Winds in the planetary atmosphere cause the gas to move as well. Therefore, you'll get Doppler shifts. And then the planet's rotation. So you should have an approaching and a receding limb of the planet, and you'll get Doppler shifts from each of those, which should lead to some broadening of your spectral lines, just like rotational broadening in stellar spectra. And then we also need to contend with the fact that there are going to be Doppler shifts in the stellar spectra that might kind of muddy some of the planetary effects. There's the radial velocity induced by the orbiting planet. There's the so-called Rossiter-McLaughlin effect because the planet is blocking different portions of the rotating velocity profile of the star as it transits. So we need to account for all of these effects. In the work that I'm going to be showing, we're going to assume that the observers know what they're doing with removing the known stellar effects. Although we're starting to work on that a little bit more carefully now. Okay, so what have we done? We took a 3D GCM, a 3D model of the hot Jupiter atmospheres, and we've coupled it now with a radiative transfer post-processing code. So we basically strike 1D rays through the atmosphere and sum together the contribution from the intensity from all those different rays to get the emergent spectra, either in transmission or thermal emission geometry coming from the planet. And we self-consistently are treating the 3D nature of the planet and the wind velocity structure of the planet. I'll give you a little bit more, a visual of how this works right here. Okay, so this is transit geometry. So I'm looking down on the top of the atmosphere right now. So these red lines are breaking up the planet on a longitudinal grid. The black lines are breaking up the planet's atmosphere on an altitude grid. And in transit geometry, I'm just striking all of these individual green rays coming from the star through to the observer, through the atmosphere. And I do the radiative transfer. In each grid cell, from the 3D model, I have a local temperature, I have a local pressure, I have a local composition, which tells me the local gas opacity, and I have a local line of sight velocity I have the 3 components of the velocity vector that come out of the GCM. I have a local line of sight velocity that I use to Doppler shift the opacity in that grid cell appropriately. So we're correctly accounting for the 3D nature of the planet entirely. In thermal emission geometry, now I'm looking at the light that's emitted directly from the planet. So I'm just solving the transfer equation in thermal emission for many individual rays extending out of the atmosphere at the observer. Okay, results. We have lots of results. I'm going to go through these kind of quickly, but stop me if you want any more clarification, or I can answer more questions at the end. Okay, so the first thing that we looked at was trying to understand this potential 2 km per second blue shift in the Snellen et al. Result for HD209. We took a canonical hot Jupiter GCM model and just wanted to look at what the transmission spectrum, what the transmission spectrum should look like, and whether or not that would lead to a 2 km per second blue shift, or a 5 km per second blue shift, or a 0 km per second blue shift. Yes, exactly. So this is like these maps are like Earth maps. Latitude, so that's the equator. Latitude, longitude, substellar point is in the middle, and that should stay consistent for all the maps that I show. So this is a slice through at a millibar pressure. Oh no, sorry. This is at 60 microbars. So this is even a little bit higher up in the atmosphere. The arrows represent the wind velocity vectors, and so you can see this day to night flow across the terminator, which is the region that we're going to probe in transmission spectroscopy. And we looked in this paper. We looked at just the canonical hot Jupiter GCMs versus ones that we had added in an additional drag term that should come from that would arise from magnetic fields, a prescription for magnetic fields. Yep.
What are the colors?
Oh, sorry, these are temperature. Those aren't labeled. That's temperature in Kelvin. Yes. What are they? So I take the local temperature and pressure that comes out of the GCM. I calculate thermochemical equilibrium for solar composition. So we've only done this, and the chemistry, if you can even call it that goes into the GCM is also assuming solar composition. Oh, there could be a core, but that's kind of decoupled from the atmosphere. Well, I mean, giant planets in the solar system have cores, and they still have metal enhanced atmospheres. So I mean, if anything, I mean, we have measured metallicities of hot Jupiter atmospheres, and they've all been consistent with solar or supersolar metallicities. The momentum balance happens deeper in the atmosphere where you can't probe it directly. So yeah, it's all about which layers we're probing. Okay. These are same models. So 2 cases where we've added this magnetic drag term, two nominal cases. These are kind of Doppler maps of the line of sight velocity at the terminator. So you can see that we expect, so we get lots of blue around the terminator. So we expect that most of the flow is day to night. This is just what I was telling you before. And then you can see a little bit deeper in, you can see that super rotating jet, the flow from day to night and then night back to day on the other side. Okay, so we generated a model at very high spectral resolution using the techniques that I was just telling you about. Here are the spectra that came out for the 4 different cases, the 2 without the extra magnetic drag and the 2 with magnetic drag. And it's probably hard to see, but maybe you can tell. Okay, so in the black is an unshifted, a non-Doppler shifted version of these spectra. You might be able to tell by eye that all of the colored lines are a little bit blue shifted relative to the rest frame spectrum. And now we're going to do what the observers do, which is take the models, take the Doppler shifted models and cross-correlate them against the 1D rest frame spectrum. So we did that here. And here's a blow up. So here's the peaks of the cross correlation functions, and we match up with that Snellen et al. Result almost exactly. The two nominal hot Jupiter models produce, based on the full complex 3D wind structure, the cross correlation velocity that comes out is exactly -2 kilometers per second for the nominal hot Jupiter models, and a little bit slower for the models with magnetic drag because the flow is slowed down. So we are expecting now, our prediction is that you should get blue shifts in these spectra due to winds on order 1 to 2 kilometers per second. We did a more careful grid-based study looking at at the wind signatures of planets with a range of level of irradiation, so hot planets to cooler planets. So here's our hottest spectra, coolest spectra. These are temperature pressure profiles that go with those planets. And what we find is that the hottest planets are going to give you the largest blue shifts from winds. They have the most vigorous day-to-night circulation, as you might expect, up to a magnitude of something like 3 kilometers per second. And then as you go to the cooler giant planets, down below irradiation temperatures of 1,000 Kelvin or cooler, that day-to-night flow becomes probably basically undetectable. And again, this is a testable prediction, so you might imagine doing a study like this for planets with a range of irradiation temperature and look for this trend. Okay, that's just showing the Doppler. This is showing the Doppler map of the same set of planets now. So you can see, again, that the hottest ones have the most vigorous day-to-night circulation. We've now compared our 3D templates directly against the observations, right? Because we can now do these calculations basically self-consistent with the prediction of the 3D atmosphere. So those, in principle, should be a better cross-correlation template than the ones that the observers have typically been using that are just based off of 1D models. And so we're testing this now. So this is the work of Erin Flowers, who is now a grad student at Princeton. She worked with Emily Rauscher and I when she was an undergrad. And okay, so this is for HD 189 733b. This is the planet's radial velocity and the planet's rest frame velocity when the data, the transmission spectrum data, are compared against the 1D template. And we know, again, where the planet should lie. We know the planet's orbital motion, and then in principle, its rest frame velocity should just be 0. So the signal should lie right there, but instead it lies over here. And so we're again seeing the spurious 2 kilometer per second, 2-ish kilometer per second blue shift that we're attributing to winds. Now let's use the 3D templates instead, and we line up much better. So the 3D template, because it already self-consistently includes the winds, recovers the 0 kilometer per second rest frame velocity of the planet correctly. And actually gives us a slightly more significant recovery of the planetary signal. And this is, I want to point out, this is especially impressive because the models that we used as our templates, they're not tuned in any way, right? We just took the input parameters of the planet, its radius, its gravity, its level of irradiation, and we just ran a GCM, and we recovered the planetary signal to high significance. We could have done a study in more parameters and done more retrieval, but we literally just ran forward models that we thought would mimic the planet, and they did great. We've looked at some higher order effects. So, for example, what would the Doppler shift signals be as a function of orbital phase for the transmission spectra of hot Jupiters. And so this is what you get with the combined effects of orbital motion, rotation, and winds. We know the orbital motion of the planet, so we can subtract it off. And so what we see is that through transit, you get kind of a constant 2 kilometer per second, 1 to 2 kilometer per second blue shift from the winds. But during ingress and egress, because you only basically have one limb of the planet in front of the star at a time, you can basically sense the orbital. You can directly sense you can directly sense the rotational velocity of the planet by looking at that rotational motion of just one limb versus the other. So this could be, this would certainly require 30-meter class telescopes to get any signal out of ingress spectra or egress spectra because of the shorter time period and also much less of the planet is in front of the star. But you could potentially directly measure the rotational velocity of the planet and actually test whether or not these planets are tidally locked. This would be one interesting way to test the tidal locking assumption. We also looked at whether or not you could sense vertical wind shear. Stronger lines in transmission spectra originate from higher up in the planet's atmosphere, and weaker lines originate from deeper in. So if you could do a mask and just get the cross correlation of the stronger lines versus the weaker lines, that should allow you to sense the velocity field higher and lower in the atmosphere. So this is a simulation for what you would expect. In the standard hot Jupiter model, we expect the stronger day to night winds to originate higher up in the atmosphere versus our models that included the magnetic field drag component. We expected much less vertical wind shear. So this is another potentially an indirect way to probe the presence of magnetic fields. Yeah, back to this, the tidal locking assumption. We wanted to push on that a little bit and see if there was a way through both phase curves and high resolution spectroscopy to probe the assumption that these planets are tidally locked. So we ran a suite of models with the planets more slowly rotating. So basically half of the rotational period of a tidally locked planet and double the rotational period of a tidally locked planet. So we could see if there's a way to detect or to sense the rotation rate of the planet directly. Interestingly, for the slowly rotating hot Jupiter, we found that the super rotating jet it collapses or basically turns around. So you get a jet instead moving in the opposite direction for the most slowly rotating hot Jupiter models. And that's going to lead you to have your hotspot of the planet shifted to the west rather than the east. In high-resolution spectra, we found that the fastest rotating model was the easiest one to distinguish because it produced more blue-shifted spectra than the slowly rotating or tidally locked models. So the idea is to put both techniques together. If you can get a phase curve and high-resolution spectroscopy of the same object, you could tell if it's rotating slowly due to its phase curve behavior, due to seeing a westward shifted hotspot rather than an eastward shifted hotspot. You could tell that it's fast, that it's quickly rotating because you would see a larger magnitude Doppler blue shift. So between the two different observational probes, you can potentially constrain if the planet is slowly rotating, fast rotating, or consistent with being tidally synchronized. We applied this to, again, the same data set that I was showing before. Again, Aaron Flower's work on HD 189733b to see if we could probe the planet's rotation rate through the high resolution spectroscopy. So now we're fitting for, now our template. We have templates that are rotating at many different possible planet rotation rates, and we're trying to fit for the planet's equatorial rotation velocity, and again, the RV semi-amplitude, which we know. So if the planet's tidally locked, it should line up here. This is the comparison against the 1D template spectrum, and it's consistent with being, the planet's consistent with being tidally locked, and it looks like you get a nice tight constraint on the rotation period of the planet. It's consistent with being tidally locked, and it's inconsistent with rotating too fast or too slowly. It's rotational velocity, so too fast or too slowly. The 1D spectrum is tricking us. When we use the 3D template, we don't get as tight a constraint on the rotational velocity, and that's a real effect. So when we use the 3D template, we still can rule out the fast rotation rates, but we're consistent with tidally locked, and we're consistent with slow rotation rates. And the reason for that is that the real atmosphere has winds. We expect it to have this circumrotating, or we expect it to have a super rotating jet. And so even if you slow the planet all the way down to rotation periods, or it's basically not rotating at all, you're still going to have the atmospheric dynamics. So you're still going to have something that's broadening. You're still going to have the jet that's broadening the spectra. So we can't actually constrain slow rotation through Doppler shifts alone. But the phase curve data rule out very slowly rotating cases, as I just showed you in the test case before, because we don't see that westward shifted hotspot. So again, between the two metrics, we can say that this planet is consistent with being tidally locked, but we do have a range of possibilities of its exact rotation period. Okay, that was all transmission spectra. Emission spectra, thermal emission spectra. We wanted to look at whether or not there would be detectable signatures of atmospheric dynamics in high-resolution thermal emission spectra. This is the work of Jisheng Zhang, who was an undergrad at Grinnell and is now a grad student at the University of Chicago. He solved all of the really nasty radiative transfer or really the nasty geometry to strike the 1D rays, the line of sight 1D rays through the 3D atmosphere. The problem is that the latitude-longitude grid is radial. The 3D grid is radial, but we want to strike line of sight rays. So each line of sight ray, they don't just go out along one longitude. They encounter many different longitudes as they strike through the planet. So it's really ugly, but he did a great job, and he solved all the ugly geometry, so we can now generate spectra from these objects. This is just again one of these temperature maps. Okay, and you can see he's added these Doppler contours, so you can see contours in Blueshift and Redshift on the eastern and western limb of the planet. So that's coming both from the rotation of the planet and the fact that the jet is also moving in the same direction as the rotation. So you might expect that you wouldn't really get any Doppler signatures from these objects because the two sides are pretty symmetric. You have redshifted gas and you have blueshifted gas, and you're seeing one whole hemisphere of the planet. But because we're looking at thermal emission, we're going to be weighted most heavily towards the hottest point on the planet. The emission is going to be weighted most heavily towards the hottest point on the planet. So when the hot spot is approaching you, what's going to happen is you're going to tend to see a blue shift, and when the hot spot's receding, you're going to tend to see a red shift. All right, so here's what some of his spectra look like. So this is for HG 20945AB as a function, spectra as a function of its orbital phase. These are the rest frame spectra. These are the Doppler shifted, and you can see that the Doppler shifted spectra are considerably Doppler broadened due to the rotation and the jet, but there are also some pretty considerable blue and red shifts, which might not be apparent from this plot here, but I'll do the cross correlation thing next as a function of orbital phase. So here, this is the cross correlation velocity signature of this planet, and you can see that you get a strongly redshifted peak when the hotspot is receding and a less strongly blue shifted peak as the hotspot is approaching you. It turns out from geometric considerations, you get your strongest velocity signature when the hotspot is at about 45 degrees off from the substellar point. When the hotspot's all the way on the limb, it's directly approaching you, but also you don't have a lot of solid angle. When it's right in the middle of the planet, you don't have any Doppler shift associated with it, so it's about 45 degrees off where you get the maximum signal, and that's what we see here. So that's kind of setting where the maximum and minimum of the Doppler signature is. And again, for this case, or for these 3 planets, we expect Doppler signatures of kilometers per second. Okay. All right, with my remaining time, I'm going to talk about one of the things that we've swept under the rug, and that's aerosols. So aerosols exist in every atmosphere of every planet in our solar system, both clouds and haze. I'm just going to go through terminology really quickly. So when I say cloud, I'm talking about something that is directly condensing out of the gas phase, and then if you heat it back up, it'll go back into the gas phase. So like our water clouds, those are clouds in our atmosphere. Haze is something that's being formed by chemistry, often photochemistry, forming involatile solids, so things that are not going to easily return back to the gas phase. Think Titan's haze, potentially think Venus's sulfuric acid haze that comes from photochemistry, and then aerosol is the blanket term that covers both clouds and haze. Right, so these things exist in exoplanet atmospheres, and they are hard to, it's easy to determine the presence of an aerosol. We've seen this many, many times in transmission spectroscopy. We see muted spectral features because there's some sort of aerosol high up in the atmosphere that is causing the stellar light not to get in as deep as it otherwise would. But it's really hard to figure out what those aerosols are. It's been almost impossible so far, and part of that is that the spectra of aerosols are, they tend, if they have features at all, they tend to be very, very weakly wavelength dependent, or they don't have any interesting wavelength dependency in the wavelength ranges that we can observe right now. Also, you tend to get degeneracies with things like particle size distribution and vertical distribution. So we just haven't been able to make a lot of headway. What are these aerosols? But planets are 3D, and maybe we can take advantage of that in some way. So we proposed a kind of toy model idea that I think works out really nicely for trying to distinguish the aerosol formation mechanism on the most highly irradiated hot Jupiters, and that's by looking at the 2 different limbs separately, which you can probe in ingress and egress. For a highly irradiated hot Jupiter, for an ultra-hot Jupiter, the day side of the planet is going to be so hot that nothing can condense, nothing at all can directly condense in its atmosphere. Everything should be in the gas phase. And so but the day side of the planet is irradiated by the UV from the star, so you can form haze on the day side of the planet. Cannot form clouds, can form haze on the day side, and then atmospheric dynamics will take that haze and transport it over to the limb on the evening side of the planet. On the night side of the planet, it could be cold enough that clouds can directly form. So you can form clouds on the night side of the planet and also on the cooler morning terminator of the planet. So you expect clouds on the morning terminator, haze on the evening terminator. They're separate from each other. They're spatially separated from each other. All right, so we generated this is just pseudo 1D models where we've taken 2 different 1D profiles, one that has aerosols, one that doesn't, and we've placed them on the 2 different sides of the planet to show that in ingress and egress, the side of the planet that has the aerosol is going to have the more muted spectral features. So if you could obtain an ingress spectrum and an egress transmission spectrum, difference the 2, you could figure out which side the aerosols are located on, and therefore hopefully constrain whether it's haze or clouds that is forming. This was a model that we applied to the ultra-hot Jupiter, WASP 121b, and we found that the difference should be of order 100 parts per million between the ingress and egress transmission spectrum. And that's even potentially doable with HST right now with enough allocation of observing time, and definitely doable with JWST. We had a student, Victoria Di Tommaso. She's starting grad school at Harvard next fall. She's a Fulbright fellow right now. She worked with us again as an undergrad. She ran models of this type, but for using the full 3D GCM, where we've added in a way to paint on physically realistic clouds on whatever location of the planet we want to. So she's added in clouds to the GCM on the eastern limb versus the western limb, and we see the same thing from the full 3D model, that the side of the planet that has the aerosols produces the much more muted spectra, and also actually a deeper transit because the planet's getting optically thick higher up in the atmosphere. I'll finish up with this is like hot off the presses. Also, this is my fun movie. We have an undergrad at University of Maryland, Caleb Harada, he's taken now, we've added the clouds directly into the GCM, so they evolve with the GCM. They evolve with the atmosphere radiatively. So the radiative feedback from the clouds, basically, we check for a condensation criterion at each time step in the GCM. If the clouds condense, we add them in, we add in their opacity, and they now feedback radiatively to the evolution of the GCM. So these are self-consistent. This is a kind of a self-consistent cloud treatment in a GCM for the first time ever, and we want to see how that impacts the observable properties of the 3D atmosphere. We have hints that this is happening in hot Jupiter atmospheres, and it might be seriously impacting how we're interpreting the phase curve observations, in particular of hot Jupiters. So this is just a clear atmosphere versus one where we've added in the clouds with the radiative feedback. You can see that it's kind of what this should be kind of apparent how to read this, but the kind of more grayed out the area is, that's the cloud opacity. So that the more clouds there are, and then the thermal structure is just shown in the temperature or in the color bar. So you can probably see that the thermal structure of the atmosphere has changed by the addition of the clouds. This is the first time that we've seen this. Other modelers have added in the clouds at the final step of the GCM, so they haven't included the thermal feedback, but it turns out the thermal feedback is really important. The thermal structure has changed, and then the clouds are present as well, and that's going to impact the radiative transfer through the atmosphere. That's going to impact the spectrum that comes out. So I'm not going to show you the spectra yet because he has them, but we're still validating the final results. But I can tell you that the cloudy atmospheres produce very different results, both for the phase curves, which is already published, and also for the high resolution spectra versus the clear atmosphere, and even versus the post-process clear atmosphere where you just paint the clouds on at the last stage. So this is pretty important, I think, and we'll be seeing more results soon. All right, so where are we going with all of this? There is a very nice case to be made that we should observe atmospheric dynamics with high-resolution spectroscopy with large telescopes, very large telescopes, like 30-meter class telescopes. So there's a key science program initiative underway to kind of spell out what those key science projects should be for, in particular, the US-based ELTs, so the GMT and the TMT. This is in the push to try to get funding ultimately from the NSF to help us pay for these telescopes. And so this is one of the, I authored this along with Diana Dragomir, and we had a larger team who worked with us. We put together a key science project proposal for exploring the atmospheres of irradiated planets at high spectral resolution. And one of the key science motivators was probing atmospheric dynamics. Right now, we still, the observations that I showed you, and if you notice, we're really only of 2 planets. And there's a small handful of hot Jupiters that we can probe for atmospheric dynamics right now with the largest telescopes and the best high resolution spectrographs, but we really need more light gathering power, and we're going to be there sooner rather than later, I hope. Okay, so takeaways. We have two techniques to probe 3D structure of hot Jupiter atmospheres, phase curves, and high-resolution spectroscopy. We can use the high-resolution spectroscopy to measure Doppler signatures, which can directly probe wind speeds, orbital motion, rotation rates, hotspot offsets, and potentially get us a handle on the aerosol properties directly or more directly. The observations are only as good as the model templates that we use to do that cross-correlation at high resolution, and so the modeling is very important. And then the 30-meter class telescopes are going to be, I think, really pivotal in pushing these techniques forward and making the measurements that we want to make. So the big picture goal, again, is that we want to understand the properties of these exotic, highly irradiated planets as a way to more deeply understand planets, planet formation, and planet evolution in general. Thanks.
I wanted to revisit this question in some of this composition.
Sure.
Precisely because of your aerosol section that I was asking that question. So at these temperatures, not forming elements in waves.
Mm-hmm. Right.
So how do you put those elements in this structure? Very important. Go back to revisit that structure and how
Yeah, luckily, I mean, so most of those, most of the rock-forming elements, most of the refractories are, they would be minor opacity sources in the atmosphere. When you're condensing out major opacity sources in the atmosphere over the temperature range of interest, that's where you need to be the most careful of how you treat that. So, I mean, yeah, these planets are hot enough for like sodium and potassium to be in the gas phase. Some of them are kind of on the border, though, of where titanium oxide should be a major optical absorber versus not. And that's one of the transitions that you have to be really careful about, because that completely changes the atmospheric structure when you take away a major optical absorber. For the I mean, they should still end up. They should still end up in the gas. Yeah, I mean, I agree that they're mostly that they're more sequestered in the core, but you should still. I mean, some of those metals still wind up in the gas phase, either through direct mixing, or because of the when they were accreted, right? If they were accreted when the planet was already had, if you're accreting like rocky planetesimals late in the formation history, they're coming in and getting bladed in the gas phase part of the atmosphere. So the models say that even though most of the metals are in the core, you're still going to get potentially. The prediction is that you should have still supersolar gas, at least stellar composition, if not superstellar composition, metallicity gas up in the atmosphere. Mm-hmm. Because you can still accrete rocks late in the formation process. Okay. Yes, for these objects they should be. Mm-hmm. Yeah. So that's, I mean, so also you remix the material upwards. Yep. So the clouds, these clouds are based on, so this is, we're still keeping the atmosphere at solar composition. So these are the species that would condense out in an atmosphere of solar composition, but at, at temperatures of 1500 Kelvin, 1000 Kelvin. Yeah. Yeah, I mean, so titanium species, iron. We have a set of 5 or 6 that are. We're following all the species that should condense out in solar composition at that temperature range are in here. They're tested with the observations that we're taking right now. So actually that's one of the problems that I should have pointed out way back at the beginning is we've taken a GCM that we know works well. They're adapted from solar system GCM. So it's either a GCM that worked well for Jupiter or that worked well even for Earth, and now we've taken it all the way. Yeah. So yeah, if you push them back, so most of them they're adapted from models that started with that heritage. So yes, that was where they were tested. They're not tested in this regime yet. The best way that they're tested in this regime is that they seem to all agree with each other, even though they have very different heritage. But now we contend with the data.
Can I ask you a question about the radiative? So a number of these hot Jupiters have been detected not in transit, but by the same high resolution.
Yes, yeah, I glossed over that too.
So how nightmarish is the radiative transfer in that case?
Oh, it's fine. It's fine.
It's fine?
Yeah. So we. It's a little, the geometry is a little bit annoying, so we're actually working right now to take the model that we've assumed transiting geometry for all of them, and now we're taking the planet and allowing it to have a non-90-degree orbital inclination. And so the ray striking, we have to mess around with the geometry even more. Yeah, but it's just a geometry nightmare. It's not other than that, it's not a problem.
And so how much better can you do for the non-transiting planets? I would think that you would have much more, because the geometry is more complicated, you also have much more purchase on the Doppler shifts.
Yeah,
From parts of the orbit.
We're working on it right now. And the main advantage of looking at the non-transiting planets is because you're directly detecting them, so it doesn't matter if it's transiting or non-transiting. There's more of them. There's more of them that orbit bright stars, but you're losing the strong handle on the inclination. Well, I guess you can probably get the inclination back out because you're treating it as a double-line eclipsing binary. So you should be able to get the actual inclination of the planet back out again. And you can potentially take advantage of the different geometries, the different orbital geometries. So yeah, we're playing around with this right now and trying to see what we can get out of the non-transiting planets. And you still need something. You still need to exceed a condensation threshold. So for these ultra hot planets, they're so hot that if you just look at what temperature range, what temperature pressure range, even iron can condense over, it's too hot. So motions shouldn't help you. Dynamics shouldn't help you. Yeah, these ultra hot planets are, so for the line is basically anything that has a equilibrium temperature over like 2000 Kelvin. It's not, they're you almost think of it as a star. It's too hot. It's too hot. Yeah, the cloud formation. Aerosols are problematic, and they're hard to treat in models, right? Because of these complicating effects, and you can have supersaturation. You need cloud condensation nuclei, and it's a huge microphysics mess when you really try to attack the problem. So in exoplanets, I think we're still at the stage where we're doing things like, is the condensation threshold, have we gone past the temperature pressure, or the condensation curve? Clouds form. And clouds form at that location right where you exceed the threshold. But we know from Earth, we know from planets in the solar system, it's more complicated than that. So we need to push the models along. We also need to contend with the data in a first order kind of way first before we just throw a lot of extra complexity at it. We need to make sure that we're kind of on the right track.
Let's thank Eliza again for great talk. She'll be at lunch if you're not on her schedule and you want to be.
Okay.